That's all right. Take the time you need. I'm ready to start. Can you? All set. Okay. I'm here to talk today about our MSc in Robotics and Autonomous Systems here at the University of Lincoln. I'm Charles Fox. I'm the program leader for this MSc course. It's a one-year program which can be taken by Lincoln students as a fourth year or by people from outside coming for the year to do the MSc. I live in Lincoln as a senior lecturer in robotics and automation. I lead the program on robotics and autonomous systems. A little bit about me to begin. So I studied computer science at Cambridge, informatics at Edinburgh, and robotics at Oxford. I have worked previously as a high-frequency hedge fund trader, as a data science consultant, and as a researcher around robotics and AI and cognitive science in various places. So I'm currently involved in several research projects, including game theory for self-driving cars. We're studying how self-driving cars should interact with pedestrians to ideally avoid ever having to hit them, but while still making some progress on the road. I also work in agricultural robotics. This was the IBEX project. This is an autonomous robot for spraying weeds in grassland. We also do robots for crop care in fields of wheat, including using large tractors and smaller robots similar to the IBEX platform. So if you're interested in my publication list, you can find it over here. And it includes my book, Data Science for Transport, which came out a couple of years ago. But I'm really here to talk about the program itself. Robotics is a very exciting and up-and-coming field at the moment. There are many applications of robotics, such as illustrated down here: self-driving cars, autonomous tractors, service, manufacturing robots. It's a very large growth area. Robotics is also a very interdisciplinary subject. We attract students from many backgrounds who enjoy coming together to share their ideas, to share their skills and experiences and bring them all together. To build a robot system, you need a lot of skills, primarily computer science and mechanical engineering. So computer science for the algorithms and the AI, mechanical engineering to make the physical robot. Usually some electronic engineering to interface the software with the physical robot. But we also have people coming in from further afield, from fields like cognitive science, psychology, philosophy, all contributing to the AI side. Biology and neuroscience can link into the neural network ideas that power a lot of our robots. Product design sits close to the mechanical engineering in many cases. And then subjects like economics, business, finance tend to have a lot of quantitative components about decision making and how to solve problems in optimal ways, which can be automated in a robotic system. But we even go out and talk to people from, say, architecture and geography. I have projects running at the moment where we're working with people like that to figure out how robotics can exist in a human environment and how those environments could be designed to make life easier for the robots. So we have a very interdisciplinary field here. We try to have students learn as much from each other as from the lectures. If people are coming from all these backgrounds, that's a lot of knowledge and skills that can be brought together. Many of the best new research ideas and commercialization ideas can come from these unexpected meetings between people of different backgrounds. To apply for the program, you're going to need a 2-1 in a relevant subject, which is usually computer science, engineering, or one of these allied subjects. And we also need to see evidence of your programming skills in some form. That can be evidenced by sending us a copy of one of your projects, a link to your GitLab if you have one, or a reference from your employer or your university tutor to confirm that you have some basic programming skills. So why would you want to study and work in the field of robotics? Primarily because robots and autonomous systems are taking over the world, not in the form of AI overlords, but in the form of an economic power that is very rapidly replacing many other jobs and careers. So a recent study from my old Oxford group in 2013 went out and asked a bunch of people whether they thought their own jobs were at risk of automation. And this very famous result, widely reported in the international media, came out that 47% of all current jobs are now at risk of near future automation. So really, if you're considering a career in almost any other field, you can be at risk of being automated by the people who choose a career in robotics and autonomous systems. So this includes both obvious physical cases in manual work, replacing human drivers of cars and tractors, people working in food and service, construction, manufacturing. Less obviously, automation of careers in white-collar office jobs, things like finance and accounting, law and management, which are using many of the same automation techniques. But the same authors of this study went on to suggest that losing all these jobs is not necessarily a bad thing, because it tends to be the more boring and repetitive parts of jobs, or even the more boring and repetitive whole jobs, which are going to be replaced. It's the things that humans don't generally want to do if they had a choice of doing something else. And that something else can now be an exciting career in robotics itself. You can become one of the people who is doing this automation and this replacing. And we hope that through that process, many new types of work will appear. We can move everyone up the value chain, away from these tedious, repetitive chores and into much more creative robotic engineering careers. So let's look at some examples of this in action. Human driving has been a career for many people for many years, and we are seeing autonomous vehicles come onto the road to replace many of those posts now. For example, this is an autonomous self-driving minibus that we ran as part of a European Union project called City Mobile 2. So I was involved in doing some of the pedestrian recognition and tracking on this system. And we successfully ran these vehicles around 2 European cities in France and in Greece for about a month each, and they successfully transported people to work like a regular bus would do. We're also seeing smaller versions of this, self-driving cars. We're seeing larger versions of it, automating trucks, lorries, very rapidly coming onto the roads around the world. So these systems, they work with fairly standard sensors. Nowadays, you will learn how to build a rig made out of these sensors during our MSc. So things like LiDAR scanners on the vehicle, stereo cameras, inertial measurement units, and algorithms for localization and mapping, which are also taught within the MSc. So similar processes appearing in agriculture. Lincoln is in one of the physical centres of the UK for agriculture. We're the heart of the UK's agriculture industry. Many of the vehicle and mechanical agricultural companies are physically very close to our university, and we collaborate with a great many of them. So agriculture is a particular interest here at Lincoln. Many of our students are doing projects in this area and working with those companies. So here, for example, we see a driverless tractor running similar algorithms to what we've seen on the self-driving cars. Different considerations. Safety is a much larger consideration when you're working with very big, heavy machinery like this. Other agricultural automation systems use small robots like the IBEX system that I showed you. sometimes you could consider replacing a single large tractor like this with a fleet of smaller robots all working together. That can be better for the soil. It's not compressing the soil as much as a large tractor would do. And you can study new algorithms for collaboration and swarming behavior in those fleets of small robots. But we're seeing automation in all parts of the agricultural cycle here. Everything from planting the seeds, monitoring the crops, putting on fertilizers, herbicides, all the way through to harvesting, trying to automate each of those stages. If we continue going through the food chain, we're seeing automation beyond the agricultural field and going out into the food processing, both the factories and cafes and restaurants, using systems such as this robotic meal maker here. So traditional industrial automation takes place in factories with conveyor belts and production lines. Many of the techniques we teach on the MSc are appropriate in those settings, but we're also seeing this much more precise customization version of robotics in the food industry. So here's a robot that is preparing one meal as a human chef would be preparing it. Now that means that every meal can be a little bit different. Every meal can be customized to what the customers are asking for. That's different from the traditional process of making 50,000 tins of soup that are all exactly the same. So this kind of system is going to require a lot of advanced AI. Okay, on a classical production line, you can pretty much do the same movements on every robot every time. So the robot arms you see on a vehicle production line are normally just going through a pre-programmed sequence of motions. Whereas if you're dealing with highly interactive food preparation like this system is going to be all about monitoring the state of the food, looking at it with your cameras, with your eyes, and figuring out what you're going to do in response to how the food is moving around. Food and agricultural products in general can be much more natural and therefore much harder to predict their behavior than purely mechanical components like the metallic components of a car on a vehicle production line. Especially during the COVID pandemic, we are generally concerned to reduce the amount of human interaction in the economic part of the world, at least. So applications of robotics to delivering stuff to end users has become very relevant recently. So this includes both kind of last mile delivery vehicles. You might consider small robots that run around the city and deliver Amazon packages or Deliveroo pizzas to people's houses, taking the human away from the doorstep, which is a potential vector for COVID-19 transmission. You might also see this occurring in places like cafes and restaurants, where you want to remove the need for human service staff to come and make the last few meters of delivery of the food to customers' tables. This kind of technology was once science fiction, and it now exists for real in a few places in the world, especially in countries like Japan, which are culturally predisposed to robotics. It began as a gimmick. Come to our restaurant, it has robot-weighted staff. Now it's becoming much more realistic for much wider use and more safe and hygienic use. And we have robots like this developed here in Lincoln. If you visit the Lincoln Collection Museum, for example, you'll already find one of our robots looking quite similar to this, which is acting as a robot tour guide. It's showing visitors around, recommending exhibits for them to look at, telling them the backstory of some of those exhibits. In construction, this is one of the world's largest 3D printers. This can be viewed as a form of robotics, and it's printing out houses out of concrete, one layer at a time, just like any other 3D printer would do, but on a massive scale. And robotics is opening the possibility that entire buildings could now be constructed almost completely autonomously. You'll probably send in some humans to put in the finishing touches to this, putting in some of the electrical systems or painting and decorating, but more and more of that process is now becoming automated by robotics and autonomous systems. And finally, manufacturing has been the classical application of autonomous systems for many decades, such as these car manufacturing robots. Again, it's well known how to build this kind of system because these robots tend to just perform the same program over and over again without very much interactivity. So if a component is in the wrong place on a production line, the robots don't know what to do. What we're seeing now with AI systems and machine vision coming in is a much more interactive version of this, where the systems can monitor what is going on and change their behavior in response to it. So if you learn to program robot arms like this, you can not only go out and help to automate an existing style of factory, moving the arms around in a pre-programmed way, but increasingly these companies are interested to bring in your AI and machine vision knowledge to make them much more interactive. So this is why a car plant is currently highly automated, whereas a food processing plant, like the one on the right here, tends not to be. You can see there are still a lot of human workers in a food plant like this. If you ever watch the TV series How It's Made, you'll see a wonderful mixture of mechanization and automation, but also these human workers being placed all along production lines. And it's jobs like this that are becoming much more automatable now that we have more advanced AI and machine vision. There's a lot of people who are paid to stand by a production line and inspect things, often items of food coming down that line, to check if they're okay and to pick them up and move them around in certain ways, which has until very recently required that human intelligence because every product is a little bit different. Now we're seeing AI and machine vision coming in. Much more of this is going to get automated very soon, maybe by you. But it's not just physical stuff that's becoming automated, it's also these so-called white-collar jobs, the finance, accounting, management, careers that are traditionally seen as good graduate careers, are all starting to fall and to be replaced by computer scientists and robotics and autonomous systems trained people. So, for example, I used to work as a hedge fund quant. I was sitting in a room somewhat like this, watching stock prices, but rather than trading them myself as a human, I was building data science systems to analyze them and to figure out how to trade automatically. The humans were setting up the ideas and the algorithms, and then they're executed at very high speeds by these autonomous systems. So human traders are becoming quite an endangered species now. You might be used to seeing pictures of trading floors with lots of humans either standing around or at least sitting in front of computer screens. Much of that activity is now just being replaced by silent computer systems, which just hum away through the day and the night, placing these trades automatically. I think it was Goldman Sachs, one of the big banks, recently announced it is going to stop hiring traders who cannot code. This used to be a nice graduate career, being a trader, but that's all going to be replaced by computer people, robotics and autonomous systems graduates. Similarly, careers like accounting, traditional accounting has been about going through numbers, looking for patterns, trying to understand what a company is doing. Accountancy has always used some forms of automation to assist accountants, beginning with the calculator to replace doing addition with a pencil. But more and more of those processes are now becoming automated. So the fun parts of accountancy, like forensic accounting, looking through company records to find evidence of crimes or fraud or malpractice, that can now be viewed more as a pattern analysis type of problems. You might have companies interested in deploying neural networks to look for anomalies in huge data sets of financial transactions to try and flag those things up automatically. So there will still be those accountants, but they'll be using skills much more like robotics and autonomous systems into the future. Management itself is becoming more automated, and there are links between the algorithms we use in robotics and autonomous systems and algorithms that are found in management science and operations research. So often we will take algorithms from those people and deploy them to guide our robots. But you can also go the other way. You can take algorithms from robotics and try and apply them out in operations research. So, for example, the system shown here is a Bayesian network system. It's using a class of AI model to infer probabilities to do with, in this case, customer purchasing decisions. We're trying to model customer behavior, who's going to buy what, predict what could happen, and then ultimately fuse that into supply chain decisions. So how much stock to buy, where to put it, in which warehouse, when to place the orders, how to move it around. This is all work that used to be done by humans, and those management decisions are increasingly being automated away, again, perhaps by you. So how do we actually teach you to do this on the MSc? Here's a map of the Lincoln MSc Robotics and Autonomous Systems program. It spans 1 year. The year is divided into 2 semesters plus a long summer project. In the first semester, we introduce all the basic concepts that are needed in advanced robotics. Again, we have students coming from many different backgrounds, whether you're computer science or mechanical engineering or something else. We need to get everyone up to speed with a set of the basic concepts. So that includes general research methods. This is shared across all our MSCs. This teaches you how to do statistics, how to read a paper, and so on. We'll start to study AI in the Advanced Artificial Intelligence module. Foundations of Robotics is beginning with the mechanical systems, what's inside a robot, building up to some basic algorithms. We go through robot programming, building simulations and real robots, learning how to write usually Python and ROS code to actually move things around. Then in semester B, we will build on those topics to go into more advanced areas. So that includes computer vision, for example, recognizing these pedestrians, advanced machine learning. Here you'll come across deep neural networks, deep learning is currently a very hot topic. We'll go to advanced robotics, looking at fancier algorithms such as interaction, and then we go to frontiers of research, which will get you up to speed with the very latest published research, whatever happens to be going on in that year. And then in the summer, you get to specialize. You can pick an academic on a topic which matches your interests and work closely with them to build your own stuff. I'll talk a little bit about each of these modules in detail. So Foundations of Robotics, this is the module that I teach on myself. And roughly it looks like this. We're starting at the lowest level of bits of wire and silicon and motors and sensors and actuators. This is the mechatronics module. You'll learn how these components work. This is the inside of the IVEX robot that I've been working on. This is how you actually build a robot, a physical robot that can move and sense in the world. So we'll study some theories of physics like mechanics and electromagnetism, the mathematical foundations required by that. We'll do some embedded systems, especially Arduino programming. You'll find used in a lot of these systems. And then the module will build on that and go into some basic algorithms that sit at a slightly higher level from this. So algorithms for doing control, for getting a motor to behave in the way you want it to behave. Kinematics and planning, that's about how you move either your whole robot around or how you move a component of a robot, like part of a robot arm, to try and get that into a position that you want it to be. So at the same time, you're studying research methods. Here you will learn how to run a scientific experiment, how to analyze an experiment, how to report it, how to do the statistical analysis that is required to make people believe in it. You know, how many times does your robot have to actually pick an apple before your reader believes that the system works and that it didn't just happen by chance? Like other fields of academic research, robotics progresses by people publishing papers. This is a scientific paper. You have probably seen these before. If you haven't, scientific papers are not written like storybooks. They are written in a very specific style. There are very specific sections. There are specific ways of writing and specific content that is expected to be found within each of these sections. So here you'll learn about how to both read and write a paper like this. What are the components of a paper? How is it put together? How do you criticize a paper? How do you find the holes in it? How do you find interesting new questions to extend into your own research? Also in semester A, you are doing robot programming. So here we're doing very practical, usually Python and ROS level programming. How do you tell a robot where you want it to go? How do you write that level of code to read its sensors, to make decisions, to control its actuators? So beginning with writing simple code to move say a wheeled robot around. How do you get it to drive from A to B? How do you get a robot arm to pick something up and move it around? Using the software that we teach, ROS and Gazebo, you can go on to build quite advanced simulated worlds such as this one. Here's a vehicle trying to navigate down a pavement around pedestrians and so on. ROS, you will hear a lot about in robotics. This stands for the Robot Operating System, and it is the standard middleware software that most robotics research and commercialization is using. So it gives you the ability to write a collection of small programs which each manage one part of the robot, and those programs can communicate with one another by what is called message passing, sending information between nodes in a ROS system. At the same time, you will hopefully pick up some good software engineering practices in robotics. There are specific forms of software engineering that are useful in robotics that you might not have seen before, or that are less relevant in other fields. So you'll learn things such as continuous integration, continuous deployment, how that gets applied in the world of ROS nodes. Usually when you build a robot system, you don't do it by yourself. You have a bunch of programmers who are each responsible for one of these components, and you have to learn how to do that software engineering together to make sure that your systems will stick together and work in practice. Then you'll take the AI module. This is largely about probability theory, Bayesian approaches to AI. This is Bayes' theorem, which tells you how to invert probabilities. If you know the probability of B given A, you can turn it into the probability of A given B. And this is really the fundamental equation which drives most of modern robotics AI, because it tells you if something in the world caused something in your sensors, you've seen the thing in your sensors and you want to work backwards and say, what's the probability of that thing in the world? Now, I've seen a black blob move along the sky. What's the probability that it was a plane? And what's the probability that plane was at a particular location? So here you'll be studying probability theory, Bayesian theory, so-called Bayesian networks. This is a Bayesian network. This is how we take that theorem and we build it into much larger AI systems. You'll probably study a lot about burglars and earthquakes. Burglars and earthquakes are two things that could make your alarm go off in your house. And if your burglar alarm goes off, then your friends John and Mary might call you and say they think they heard your burglar alarm going off. And if John and Mary have both called you and said they think your burglar alarm's going off, what's the probability that your house has in fact been burgled? Or what's the probability that an earthquake has taken place? And the Bayesian network is it's a nice way of growing systems like this with these probabilistic semantics. You can imagine extending this network with many more nodes, modeling all kinds of entities in the world and making AI inferences about them. And you'll see the probabilities flow around the network, around these arrows. When you build Bayesian networks that run over time, you will get classes of models called hidden Markov models, Kalman filter models. When you add action, you get to Markov decision processes. And these are often used for tasks like tracking. Suppose someone else has built a machine vision system that detects pedestrians, and your task is to track them over time. So every time they tell you they think they've seen a pedestrian, but they're not quite sure, you're going to take that information and you're going to fuse it all together, and you're going to try and construct these tracks. These red lines are showing where you think the pedestrian has moved over time. So that's called a tracking problem. And you'll see these temporal versions of Bayesian networks used in all types of tracking problems like this. How do you actually get detections of pedestrians like that in the first place? That's the task of another module called computer vision. How do you go from images to understanding what is there? So in vision, you'll learn to do things like this. Take a picture of a street scene and find the pedestrians within it. This can be done through classical image processing methods, nowadays also by deep learning methods, which will link to what you do in the machine learning module. When we study vision in the context of robotics, it's a little different from how other students will be studying it. A pure machine vision student will be more likely to take images like this in a large offline collection, and they'll be doing processing on the batch of images, and they'll be trying to get their system as accurate as possible in terms of, say, finding the greatest number of pedestrians. Whereas when you go to robotics, you might have systems like this. This is a small robot with some visual sensors on it, otherwise known as cameras. When you place a visual robot in the world, it has different considerations about what is most important for it to do. It has an inherently real-time constraint. You don't have as much time or compute power, usually, to run the same kind of accuracy that offline vision can run. If you're running on these embedded systems, you have very limited computation physically available to you. But a robot like this will also have different priorities. Maybe it doesn't care so much about seeing all the pedestrians in the background. It's more concerned with not hitting the pedestrians which are immediately in front of it. It's going to want to pay more attention to things which affect it. And it's going to be thinking more about how its own actions affect the world. Now, what would happen if I drove over here and then used my cameras to get some more information by looking at these people from a different perspective? In the machine learning module, we will primarily study what are known as neural networks, or deep learning has come to almost completely dominate the field of machine learning. This is a deep neural network representation. Here is an image, such as a picture of a dog. Here are layers of neurons stacked up above that image. And lower layers of the network are finding features like edges and corners and blobs, and higher levels are looking for more conceptual features like eyes and noses and ears. And when you get to the very high level, we're looking for classes of objects, like is this a dog or a cat? You will study some more traditional machine learning approaches before this. These are things like decision trees, regression, support vector machines. The field has very definitely moved in this direction, largely because of GPU technology making it possible to run very large deep learning systems in real time. We'll get you up to speed with the latest developments in deep learning theory. These are things like transformer networks, recurrent neural networks, adversarial learning, lots of different flavors of neural net research. So this is used heavily in machine vision, but also in other types of machine learning, such as data science and big data analysis. Advanced robotics module will specialize in some of the research areas that our staff are currently involved in. At the moment, these are manipulation and grasping. This is how do we build a system like this that can figure out how to pick up objects, manipulate them, move them around, often composed from what are called movement primitives, or tiny components of motions, a single movement of a finger. How do you string those primitives together to make a full grasping plan? Some of this links into learning from humans. This is how does a human teach a robot to do this kind of thing? What can you do if a human is able to move these tins around with their hand as well, and the robot is going to learn from experiencing that, to try and learn how to do the task itself. We're currently very interested in multi-robot systems. This is a drone swarm. How does AI planning control theory change when you've got 100 robots working together? What if they can communicate with one another? What if they can't communicate with one another? How do they avoid colliding? How do they avoid trying to do the same piece of work that someone else is doing? And then finally, in the frontiers module, we'll go right to the cutting edge, wherever that happens to be in the current year. So we can't tell you what will be taught here because the current year, the next year hasn't happened yet, but we'll be getting in a series of speakers who are doing interesting and exciting things right on the cutting edge, people who've just been publishing new research in their fields. So for example, this might involve things like space robotics. There are currently many of these Mars rovers out on their way to Mars, also similar systems on their way to the moon at the moment. We've had speakers working in virtual reality on autonomous vehicles. This is showing a pedestrian interacting with in this case, a human-driven vehicle, but we're learning from those interactions about how to control the autonomous vehicle to avoid hitting the pedestrian, while still encouraging them to get out of the way. So lots of exciting virtual reality studies looking at human-robot interaction at the moment. After semester B, you will go on to do your projects. During the summer, you can work with one of our academics. Some students will work on an existing project that's happening in Lincoln. Others will work on their own project that is their own idea, depending on your interests. If you choose to join up with an existing project, for example, we have a lot of agricultural robotics research in Lincoln at the moment. Like this system is for picking strawberries, and there are many people involved in developing these systems. So we recently had a student, James, who got involved in that team and was working on planning algorithms for fleets of these robots to work more collaboratively inside a strawberry picking environment. So if you want to get involved in big science, serious cutting edge stuff that is done by Lincoln academics and our collaborators, many people here have links with companies and other universities, and they can get you out into the community if you want to join in one of these existing projects. You don't have to do that. Some students have their own ideas and they want to make their own thing. And we have some excellent projects building up in this way as well. So a nice example of this was Andrew's project from 2020. Andrew wanted to build a self-playing guitar. So this is a physical guitar. Andrew's designed a system which automates the playing of the guitar. This is developed completely from scratch. What you see here is mostly made on a 3D printer with a bunch of mechatronics components. This is the fingerboard end. This is the pick playing end. You can see there are 6 guitar picks, 1 for each string. And Andrew did some lovely work figuring out how to control all of this stuff to get the best sounding notes, to get the cost down, to get the ease of production down. This is developed as an open hardware project. So this project is sitting on GitLab, I think, right now. Anyone can download it. You can put these files into your 3D printer and build your own version of the system anywhere in the world. And maybe in future years, other students can build on this. For example, we've talked a lot about AI planning systems to figure out how best to perform particular pieces of music. Real human guitarists make a lot of decisions about which fingers to use, which strings to use. There are different ways of playing the same note, and there's some nice AI algorithms that can be sat on top of this system at those levels. This is the tool chain that most students will use during those projects. They're the same tools that are taught during the modules. So most of what we do is using open source systems. We use Ubuntu and GNU very heavily. A lot of programming is done in Python and C++. You will learn about Arduinos for embedded systems and mechatronics. Robotics integration is done through the ROS, Robot Operating System. Machine vision is usually done through the OpenCV libraries. Students also use FreeCAD for doing the mechanical designs, such as the robot guitar you saw. We're heavy users of Git for version control and for collaborative, helping students to work together using Git. We use LaTeX very heavily for our academic report writing. We also use a fairly standard set of mathematical tools. You'll need to have some basic understanding of these ideas when you first arrive. We can help you to prepare for that during the summer before you come. We have a bit of a refresher in the foundations module, but it tends to be a lot of linear algebra. That means vectors, matrices, a lot of trigonometry, rotations. Quaternions are like four-dimensional complex numbers used in rotations. We're fundamentally dealing with physical systems moving and rotating around. There's a lot of Bayesian statistics, especially Gaussians. If you come across Gaussian distributions in statistics, it's a good thing to know about. And this is how it all fits together then. You have your semester A, we get you up to speed on all the basics. This is involving working with people from very different backgrounds, mostly computer scientists and mechanical engineers, but people coming from economics, business, biology, psychology, neuroscience, all kinds of things, getting to know each other and getting to know each other's subjects. Semester B, these more advanced concepts, vision, machine learning, advanced robotics, frontiers, and your own project during the summer, either affiliated to one of our big projects or do your own thing and build your own system. If you're interested, there's more details and the application process can be found at the website. I believe we've got two of our current students, David and Harry, on this call, who are able to answer any questions you might have about the MSc. Do we have David and Harry here? I can see them appearing on the stream. Hi, David. Hi, Harry.
Hi.
Hello.
So, does anyone have any questions they'd like to throw at our current MSc students? Or while we're waiting, would either of you like to just generally talk a little bit about your experiences so far?
Yeah, I mean, it's been quite good so far. Obviously, coming from the University of Lincoln undergraduate computer science program, has been quite a nice transition because the modules I chose as well were image processing and the robotics module as well. So it's been quite an easy transition to get onto the MSc, and just generally it's been quite good actually, especially considering the COVID restrictions and everything at the moment.
So how do you find it being around mechanical engineers and people from these other backgrounds? How's the relationship between the computer scientists and everybody else?
I think it's pretty good. It's just interesting to see that much more they know about sort of like actual mechanical systems and just how much more I need to understand for me. David, do you have any like ideas on what you think?
Yeah. So part of the foundation module is that we're given, well, we were given some electronics to get started with, to mess around with. And I found that computer scientists like to just write code and hit go, but it doesn't really work with hardware, because if you break something in hardware, it's a lot more of an issue than fixing a bug and hitting go again.
There's a question coming. Was there a specific area of robotics that convinced you to take it on as a master's?
I think the robots module in general was pretty good and sort of just gave us like a lot of ideas on like what you can do with robotics and sort of like what areas you want to go into. I think it also helped that for me, especially during my dissertation for my undergraduate, I did a robotics project and sort of got myself more involved with it and sort of just, you know, it was just all kind of really interesting. So
yeah, it was similar for me actually. In my dissertation, I did a lot of open source work, which is actually something huge in the robotics community. Like with Ross, as Charles mentioned, that's entirely open source. And really that philosophy I really enjoyed, being able to make stuff that other people will actually use and is helpful.
So what would you guys imagine yourselves doing in about 10 years' time when you've become a robotic expert? Where do you think you might be working? What might you be making?
hopefully I'll be making more open source hardware projects and sort of deploying more stuff into the agricultural field of robotics for myself. Sort of, you know, trying to make sure that as many systems are open source and like hardware as well as software, so that it's all available for everyone to be able to learn from and also use as efficiently as possible.
Yeah, I'm sort of similar. I'd like to see everyone being able to have robots around the house and doing all the stuff they don't want to do, like dishes and vacuuming.
The robot butler.
Exactly, yeah.
Yeah.
Yeah, we've been doing well on vacuuming. The dishes still seem a challenge. I'd love a robot dishwasher loader. That's so annoying. Just taking them off the table and putting them in the dishwasher.
I just like a dishwasher, to be honest. But
Yeah.
we'll get there in time.
Student housing.
I mean, this is where it's useful to have these other people around as well. You know, if you try and design a robot that is only a piece of robotics, then you have all these problems about how to recognize different kinds of cutlery and how to manipulate everything. If you're able to work with a product designer, there are people who really know about cutlery and crockery, and you know, those people might be able to make your world easier if they could design a special kind of knife and fork that makes it easier for your robot to pick up. You have a much better chance of being able to do that kind of thing. So it's always a very interdisciplinary subject, I think, to do this well. And you two are both from the Lincoln program, right? You were both Lincoln undergraduates. So how have you found the transition to being an MSc? How is this kind of learning different from what you did at undergraduate level, I wonder?
It's definitely like more open-ended and sort of giving you more freedom to sort of look into stuff that you want to do. Like they give you sort of ideas on like what you should be doing for like your own research, and it's for you as like assignments. They're a little bit more open-ended, I feel, than with the undergraduate ones, so that you have like a larger amount of freedom to like decide what you want to do and how you would like to do it.
Yeah, I think there's definitely a lot more pressure on you to sort of decide what you find interesting and actually to do some background research when compared to undergrad.
Okay, there's another question coming. Is there an area of robotics you feel is advancing faster than the others?
I think definitely the vision side has come a long way recently. with stuff like deep neural nets. There's one in particular called YOLO, which is a network which is based on running fast, which is a big issue that used to be the case with using machine learning for object detection and stuff like that. But definitely in the recent past 5 years, I'd say it's come a really long way.
Yeah, that's a nice example of how robotics is different from AI more generally. If you were to study machine vision or machine learning in itself, you probably wouldn't care so much about that real-time performance. Whereas the YOLO approach to deep learning is inherently about that real-time ability. It's something you can actually put on a physical robot on an embedded GPU system and send out into a field in the way you couldn't do with most of those other algorithms. So yeah, it's not just the algorithm; it's that mixture of algorithmics and architecture and the practicality of it for robotics. How about Harry? What do you think is the fastest advancing area right now?
I'm thinking like the ML side of things, machine learning, and all that sort of stuff, because it's like you said, with the object detection, it's becoming such a lot more accurate. So therefore, a lot more opportunities are open to then sort of try the machine learning approach with. So it makes it easier to solve more problems, sort of thing. Okay.
Thank you. We've got a message. I think we should close now. Thanks, guys. So thank you both for coming. Thank you to everyone for listening. If you are interested in the MSc and you're out there, please get in touch with me or probably with any of us, and we can answer any more of your questions. Thanks, everyone. Bye for now.